welcome to Easy BTech, your guide for BTech and beyond. In this class, we'll learn about the performance of short transmission line. Performance of short transmission line. Okay. In short transmission line, the effect of capacitance is neglected. Keep in mind, effect of capacitance is neglected because it is very less. Why it is neglected? We are not consider capacitance effect in short transmission line, therefore it will give a simple calculation in short transmission lines. Okay, here we are representing three phase line with a single phase line. Okay, just a small changes in the formulas only. The representation is same. We are representing whether it is a three phase system or single phase system. We will represent with single phase system. In balanced system, three phases we are also representing with a single phase. That's why. Okay. Now I am representing the transmission line. Here we are having only resistance and inductance. I am representing the transmission line with the resistance and inductance. It is inductive reactance, this resistance, this is sending end, this is receiving end. Normally we represent the receiving end current is IR, sending end current is IS. Okay, here all the terms are in series, therefore in series current is same, therefore sending end current equals to the receiving end current in short transmission line. We have to keep in mind, and I am representing both the currents with I in the notations. I means either it is a sending end voltage or receiving end voltages. Sending end current or receiving end current. Now for the cases it is same, sending end current and receiving end current. Now I am represented some terms here. It is resistance. Resistance is loop resistance, means both the conductors. It is loop resistance. It is represented ohm per phase, and XL. XL is inductive reactance. Loop reactance. Loop reactance is also represented with ohm per phase, and VR. VR is the receiving end voltage. Receiving end voltage. Some cases, maximum cases, they are representing with the kV, and cos pi r is power factor of receiving end. Receiving end power factor. For this case, I am taking this power factor is lagging, and Vs is sending end voltage. Sending end voltage in kV, and cos pi s. Cos pi s is sending end power factor. Okay, sending end power factor. Okay, first we will see the phasor diagram for short transmission line. Phasor diagram for short transmission. Okay. I am representing this with I am taking reference vector is a current vector. Reference vector is a current vector. Taking that, this is the current vector, I'm taking this is the reference I. In lagging power factor, voltage leads the current. Therefore, I'm taking the voltage vector, receiving end voltage vector. It is VR with an angle of phi r. An angle of phi r. I'm taking it is 0. It is point A. Then next, here it is taking this I. Vs, it is VR for ease analysis. Still at R. Now Vs equals to VR plus the drop in the transmission line. The current flowing through the resistance is I. Therefore, I into R drop is there. I into R drop I represented with. It is in phase with the current. Therefore, it is same. It is I into R drop. Next, I am representing this I into XL. I into XL drop. I into XL is 90 degrees to the resistance into current. Okay, it is I into XL. It is I into R drop. It is I into XL drop. Now the total receiving end voltage. The total receiving end voltage is this is the receiving end voltage Vs. This is the receiving end voltage Vs. This is the phasor diagram of short transmission line. Okay, Vs equals to VR plus I into R drop plus I into XL drop is equal to Vs. Here also VR plus drop is equal to Vs. We are representing with phasor diagram. Now the angle between sending end voltage to current is pi s. Okay. Now I am taking O A. This is I am represented with B. I am represented, this one is C. I am represented with this one is D. Okay. Now from the phasor diagram, it is clear that, okay, I will write here. From the phasor diagram, from the triangle of OCD, from the triangle of OCD, OC square is equals to OD square plus CD square. Okay, OC square is equals to OD square plus CD square. Here, what is OD square? OD square is nothing but, we are taking this one also. I am taking this point is E. Therefore, OE plus ED whole square plus BC plus BD whole square. Okay. Now, what is OC from the phasor diagram? It is Vs square. OE from the phasor diagram, it is VR cos IR plus ED is nothing but AB is I into R drop. Therefore, it is I into R whole square plus BC is I into XL, BD is VR cos VR sin phi r, VR sin phi r plus BC is equals to I into XL whole square. Okay. Now, from this, Vs equals to VR cos phi r plus I into R whole square plus VR sin phi r plus I into XL whole square under root. This is the expression for sending end voltage in a short transmission line. If you know the sending end voltage, from that you can calculate the regulation of transmission line. Percentage regulation equals to V no load minus V full load divided by V full load into 100. Okay, in a short transmission line, this is VR, this is Vs. No load means IR equals to 0, is nothing but I equals to 0. Therefore, if it is a open circuited, the voltage between these two is nothing but Vs. Therefore, for short transmission line, V no load equal to sending end voltage, V full load equals to receiving end voltage. Therefore, this formula becomes Vs minus Vr by Vr into 100 for short transmission lines. Okay, this is the formula for percentage regulation. Now, for efficiency of transmission line for 3-phase and single phase, I am writing the formula for single phase and I am writing the formulas for 3-phase. Losses in single phase is I square into R, losses in 3-phase is 3 I square into R. The efficiency equals to root 3 Vs. We are it is single phase. In single phase, there is no root 3. In single phase, it is output by input into 100. For output in single phase is Vs, Is, cos phi s. Input, here I am representing receiving end voltage. Output is VR, IR, cos phi r. Input is Vs, Is, cos phi s. We are also having another formula for efficiency. It is output by output plus losses into 100. For 3-phase, the efficiency equals to output by input to 100. Here output is root 3 VR IR cos phi r. It is a line voltage. Root 3 Vs Is, it is a line voltage, cos phi s, or output by output plus losses into 100. Okay, this is the way we will calculate the efficiency and the regulation of a transmission line. Now we will see the problem on this short transmission line, how to calculate the performance of short transmission line by using this formulas. Okay, now a single phase 11 kV line, having length with the length of 15 kilometers, is to transmit 500 kVA, to transmit 500 kVA. The resistance is equals to resistance of the line 0.25 ohm per kilometer, and inductive reactance of the line is 0.6 ohm per kilometer. Calculate regulation, calculate regulation for 0.75 lagging, 0.75 leading, and efficiency of the transmission line. Okay, efficiency of the transmission line. Okay, here length is 15 kilometers, therefore it is a short transmission line. First we have to write the given data. What the given, what we have to find. Given data, the given it is a single phase line, point number 1, and the voltage at receiving end is 11 kV and represent with 11,000 volts. Length equals to 15 kilometers, and resistance of the line is equals to 0.25 ohm per phase per ohm per kilometer, and XL equals to 0.6 ohm per kilometer, and the given output power in kVA it is 500 kVA, and we have to calculate the regulation. Percentage regulation for 0.75 lagging, 0.75 leading, and efficiency of the line. Okay, have to calculate a regulation for 2 cases and efficiency of the transmission line. First of all, we know the formula for regulation. Regulation equals to percentage regulation equals to V no load minus V full load divided by V full load into 100. In short transmission line, V no load is nothing but Vs, V full load is VR, VR to 100. Okay, for here in above formula, we know the VR equals to 11,000 volts. We don't know Vs. Okay, for calculating Vs, first case I am taking cos pi r equals to 0.75 lagging. Okay, therefore Vs for lagging power factor. The universal formula for Vs equals to VR cos pi r. This I am taking the Vs formula. VR plus cos pi r plus I into r whole square plus VR sin phi r plus or minus I into XL whole square, where positive for lagging power factor and minus for leading power factor. We have to remember positive for lagging, negative for leading. Okay, first I will calculate for the case 1. It is lagging. Case 1 is cos pi r equals to 0.75 lagging. Cos pi r equals to 0.75, then sin phi r equals to sin of cos inverse 0.75, you get 0.6614. Okay, now the formula for Vs is VR cos pi r plus I into r whole square plus VR sin phi r plus I into XL whole square under root. In this formula, the unknown is I. We have to calculate the current I. We don't know the value of I here. Therefore, we have to calculate. We know the formula I equals to P by V for single phase. It is 500 kVA divided by V is 11 kV. We can get the current I equals to 45.45 ampere. Substitute all the values here. The root of Okay, now I will substitute VR equals to 11,000 into 0.75 plus 45.45 into the resistance. The given resistance equals to per kilometer. The given resistance per kilometer is 0.25. Therefore, we have to calculate a resistance for 15 kilometers. It is 0.25 into 15 is 3.75 ohm. Total resistance of the transmission line. XL equals to 0.6 per kilometer into 15, we can get 9 ohm for the transmission line. We have to substitute these values 3.75 and 9. 3.75 and 9. Okay. The resistance is 3.75 whole square plus VR. Sin phi is 0.6614 plus for lagging. Current is 45.45 into 9 whole square under root. We get the Vs. Therefore, Vs, after calculating this, you get Vs equals to 11,399.76 volts. Therefore, percentage regulation equals to 11,399.76 Vs minus VR by VR is 11,000 divided by VR is 11,000. This is Vs, VR, this is VR. Okay, into 100, we can get the regulation is 3.634 percentage. Okay, this is the way we will calculate the regulation for 0.75 lagging. And I am calculating case 2. Case 2 is power factor equals to, for case 2, power factor equal to 0.75 leading. Sin phi r equals to same 0.6614. Therefore, the formula for Vs for leading power factor, VR cos phi r plus IR whole square plus VR sin phi r minus I into XL whole square the root. Substitute all the values. 11,000 into 0.75 plus 45.45 into 0. It is not 0. It is 3.75. 3.75 whole square plus 11,000 into 0.6614 minus 45.45 into 9 whole square. Get the Vs is 10,865.1 volts. Therefore, percentage regulation equals to Vs minus VR by VR into 100. Okay. You get 10865.1 minus 11,000 divided by 11,000 into 100. I get the regulation is minus 1.23 percentage. Okay, this is the way we will calculate the regulation for lagging and leading. Okay, now the efficiency of transmission line. Efficiency of transmission line is output by output plus losses into 100. Here output in kilowatt, we have to keep the output is in kilowatt. Therefore the given power is in kVA. That's why output in kilowatt is equals to 500 into cos pi r. It is 0.75. Therefore, multiply with the 500, you get 375 kilowatt. Losses for single phase is I square into R. I is 45.45 square into 3.75. You get losses or 7.75 kilowatt. Therefore, the efficiency is output by output plus losses. Therefore, efficiency is output by output plus losses to 100, get output is 375 divided by 375 plus 7.75 into 100, you get 97.98% is the efficiency. This is the way we will calculate the efficiency of transmission line. Thank you for watching.